In today's lesson, looking at further optimization problems, we're going to look into inventory control. When businesses order and then store supplies or products for later use or for later resale, the size of the order carries implications. When we're working with inventory control, we keep track of two kinds of costs. The one is carrying cost. These are the costs that are associated with carrying inventory. It sounds like a funny way of saying it, but basically, if you're buying things that you put together into a product, well, you're getting all of these other things. The other people are carrying the supplies to you, then you're putting them together. You're carrying them until you sell them to the customer. That's kind of the imagery behind it, but think of it as the holding cost. These kind of carrying costs are things such as insurance, storage cost, and even taking into account the money that's tied up in your inventory. If you buy 20,000 books, well, you can't use that money. It's already been used. In fact, you probably even are paying possibly a loan, paying interest. Well, the interest would be considered carrying cost, as you're going to pay back that loan once you sell the books. Now, the implications that I was referring to is that if you order enough supplies or a larger quantity, enough to last, say, maybe half a year or a year, well, then your carrying costs are going to increase. You're going to tie up more money that's in inventory. If you had to get a loan, the interest amount's going to be higher. You'll have to buy more insurance. If you have to have a bigger warehouse, you may have to rent another warehouse, so you're going to have increased carrying costs. Well, so then you say, well, let's order in smaller quantities. Well, if you order in smaller quantity, then the ordering costs go up. The ordering costs are things that are associated with ordering the product, such as freight charges. Maybe there's a minimum freight charge. If you order more often, you don't have as many carrying costs. But if you order more often, then you may have to pay the minimum freight charge because you don't actually get up to an amount that's large enough to be the smallest amount. There's staff time to prepare and pay for the orders. If you order something once a month versus once a year, well, your staff, it takes time for them to do 12 orders instead of just one, and that is a cost. Also, the cost of receiving and checking orders when things come, to make sure things aren't broken. You check it when they come. Well, if you have 12 orders per year, well, then someone has to check receive 12 orders and also check them, versus if you did it once, it would be more efficient. So, if you order larger quantities, the carrying costs go up, but the ordering costs go down. And if you order a smaller quantity, well, then the carrying costs go down, but then your ordering costs go up because you're ordering more per year. So if that's the case, how do we optimize inventory? Well, I've already been referring to a formula, a function for cost, that when we're looking at inventory, we'd say that the inventory cost is the ordering cost plus the carrying cost. Now, just to be clear about this, the cost of inventory is different than the inventory cost. The cost of inventory is how much, let's say that you sell books, you're a bookstore. The cost of your inventory is the cost that you paid to buy the books that you have in inventory. The inventory costs are the things that are associated around your inventory, but not the actual cost of the books themselves. How much it costs to get the books here, how much it costs to store it, how much it costs to order the books, and so on. So we're talking about two different things here. For this class, we're going to focus on the inventory cost, and again, the cost of whatever it is you have in inventory is the cost of inventory, but the inventory costs are the costs associated around that cost, the ordering cost and the carrying cost. Now, if we want to maximize this, we need a little bit of background. And here's a particular problem that's also in the book. A supermarket manager figures that 1,200 cases of frozen orange juice will be sold at a steady rate throughout the next year. The manager wants to order these cases by placing equally spaced orders of the same size throughout the year. So maybe he wants to order 10 times per year, or 12 times per year, or maybe just 4 times per year. Given that it costs $8 to carry 1 case of orange juice in his inventory for 1 year, we want to find the carrying cost if the manager places 1 order per year, 2 orders per year, or 4 orders per year. Now, in working with the carrying cost, we realize that we were already given a way to figure out the carrying cost. The carrying cost is going to be the number of cases that we have times 8. The 8 comes from, or $8. The 8 comes from the cost to carry 1 case of orange juice in inventory per year. So the number of cases that we order times 8 will give us the carrying cost in this case. Now, here are 3 different graphs. We're going to focus just on the top one for here right now. The inventory in units, if we order 1 time per year, we order, question A said, ask us to calculate this based on 1 order per year. We're going to order 1,200 books. So our inventory is going to be up at 1,200. And we're going to assume that sales are consistent, kind of straight line thing. And by the end of the year, we're going to have no books in inventory. We've sold all of them. So assuming sales were steady, our inventory would reduce by a steady amount. Here, this would be halfway through the year, and so we get down to the end. Now, when we're looking at this, we realize, well, if we wanted to calculate the average inventory that we had throughout the entire year, we realize, well, the average inventory is going to be 600. It starts at 1,200, goes the whole way down to 0. We can look at it and say, well, obviously here in June 30, the inventory would be 600. I shouldn't say June 30, halfway through the year. Well, here, at a quarter of the way through the year, the inventory is going to be at about 900. Well, then at 3/4 of the way through the year, the inventory is going to be about 300. Well, take this point at 300 and this point at 900 and say, well, the average of that's going to be 600. So we realize that for every point we have on this side, there's another one below that line here. The average is going to be 600. If nothing else, think of it as if we cut off this part of the triangle of this inventory and flipped it over, it would fit perfectly into here. And then everything, the inventory throughout the whole year would be 600. So that's our average inventory level. When we're doing this, of course, a faster way than graphing to figure this out would be to simply say that if we're going to calculate our inventory cost based on average inventory, well, we just simply do x over 2, where x is going to be the number of units that we sell throughout the entire year. We were told it's 1,200. So 1,200 divided by 6, in this particular case, would tell us the average inventory is 600. Now, actually, I said throughout the whole year, that would actually be, it's not 100% right, because we're going to sell 1,200 in all of these, in all 3 of these cases. But technically, what's happening is we're taking the maximum inventory that we have, and then calculating the average based off of the amount that we ordered. So, again, the average inventory when we order 1,200 is going to be 600. Now, if that's the case, and we want to calculate the carrying cost, we said that the carrying cost was the number of cases times 8. And if we're calculating our carrying cost based on average inventory, well, then our carrying cost based on average inventory is going to be the number of cases based on average inventory. So we take the 1,200 over 2 to get 600 times 8, so it's going to be $4,800. Now, this is a method, an accounting method of calculating carrying cost that is based on average inventory. We'll see another way of calculating it shortly. Now, if we order twice per year, we're going to order 600 in the beginning of the year. That will slowly go down to 0. And then, when it gets close enough, we're going to order another 600. So we have a total of 1,200. But we realize we only have to have 600 in inventory. And once it gets low, we order again. And we go back up to 600, and it goes back down again. So in this case, our orders are 600. And if we calculate our carrying cost based on average inventory, the average inventory is going to be now 600 over 2, or 300. So the average the carrying cost based on average inventory from ordering twice a year would be 300 times 8, or 2,400. So the cost have decreased to half the original amount if we order one time per year. Now, if we continue the same thing, but we order 4 times per year, we look at it and say that our average inventory is going to be our ordering total of 300 divided by 2, or 150. So our carrying cost based on average inventory, we will do 4 orders per year to get 1,200. But the average the carrying cost based on average inventory will be the average inventory of 150 times 8 to get 1,200. It's just a matter of coincidence that works out to be 1,200 books, or 1,200 cases of orange juice, as well as the carrying cost for average inventory. Now, obviously, ordering 4 times per year is going to mean a decrease in cost, but we're only looking at the carrying cost. If we are ordering 1 time per year, our ordering cost will be a certain amount. If we order twice per year, well, that means our ordering costs are going to be twice what we would pay if we had done it once. And if we're ordering 4 times per year, it's going to be 4 times the original amount for each order. So our ordering costs are going to go up, and we need to find a balance between these two. Well, how do we do this? Before we move on, I'll mention that this method of calculating carrying cost is based on average inventory. Another accounting method is to calculate it based on maximum inventory. As in, once you make an order, what's the maximum you're going to have in your inventory after that order, or at any time of the year. Well, and if you're using maximum inventory, then you just simply use the size of the order instead of dividing it by 2 for average inventory. So hopefully this kind of makes sense. If we're ordering once per year, we're ordering 1,200. We're basing on maximum inventory. It's going to be 1,200. If we base it on average inventory, it's going to be 600. Now, we need to know more about the ordering cost to be able to calculate this. So we look at this problem. It's the same information as we were working with, which was called example 1. The manager wants to establish an optimal inventory policy for ordering orange juice. Again, 1,200 cases will be sold at a steady rate during the next year. The manager wants to send, well, same thing as before. We want to find the economic order quantity, the order size that minimizes the total ordering and carrying cost. Now, we find out that the ordering cost for every delivery, for each delivery that we do, is $75. And this we know from before. It costs $8 to carry 1 case of orange juice in inventory for 1 year. And it tells us that the carrying cost should be computed on average inventory. Now, when you're working for a company, you will know which method you're using. You'll always calculate it on average, or you'll always calculate it on maximum inventory. For the homework and on the exams, you'll be told which method to use. You just need to know whether to use X for maximum inventory or to use X divided by 2 for average inventory. In this case, we're going to use X divided by 2. Now, the ordering cost is going to be $75 for each order. So let's use R. I simply do that because the book uses R. R represents how many orders we're going to place through the year. So if we order 4 times per year, 4 orders times $75 per order will be the ordering cost for the year. And we already know our formula for the carrying cost, and it's $8 times, again, we were told average inventory. So it's going to be 8 times X over 2, and that is going to be 4X. Again, the cost times the method of inventory that we're using. Average inventory is x over 2. We multiply these together to get 4x. Now, we know that our inventory cost is our ordering cost plus carrying cost, and we have both of these now. Our ordering cost is 75R, and our carrying cost is 4x. Now, some students ask, why do they use R? Why don't they use O for ordering? Well, if you want, you can. I don't recommend it generally because if you're going to do this 75O, well, it's possible when you're in a hurry to all of a sudden have 75O become 750 just by writing the O a little bit too big or the number smaller. So if we stick with the R, you won't confuse it real quick. Say, well, what if I prefer to use a Y? Well, that's fine. You can. Just know which one is which. This is R for the R in ordering, and the X we're just using for the number that we're going to order. Now, that leads us to the last thing. This is our inventory cost, but we haven't used this 1,200 cases. Well, like we did before, we need two formulas. We have one for the inventory cost, and it's using two variables. So we need another equation. And we're given it, again, indirectly. We know throughout the year we're going to order 1,200 cases. So the orders that we place, if we place 4 of them, times the quantity per order, which is what our X is, should equal 1,200. So this is our second equation. And without knowing what it is, suppose we made 10 orders per year. Well, we know we'd have to order 120 cases each time to get 1,200 cases per year. So this is something you're never told, but it's something that you just should know. The number of orders times the quantity per order will equal something, and usually you're told what that is, in this case 1,200. Now, in identifying this, the inventory cost, that's the objective function, right? We know that for two reasons. One, we're trying to minimize this. So this is our goal. This is our objective. The second is that it's equal to something which we don't know what it is yet. That's what we're trying to solve. The other equation is our constraint because it is equal to a value. We're limited to that. Since it's equal to 1,200, it's our constraint function. So now we do the same thing that we did in the prior class. We take our constraint function and we solve it for R. We could solve it for X if you want to. Either way will work. If we solve it for R, it's in terms of X, which most students like to work with. So R will equal 1,200 over X. Then we take this and put it into our objective function, our inventory cost. So the 75R becomes 75 times 1,200 over X plus 4X. And then, of course, we do the math, the simple algebra, to get 90,000 over X plus 4X. We know that we need to take the derivative of this, so we convert the 90,000 over X to 90,000 X to the minus 1. And then we take the derivative, and we end up with minus 90,000 X to the minus 2 plus 4. We know we set this equal to 0 and solve, so we might as well change this to minus 90,000 over X squared plus 4. Now I'm going to move all of this up because I've run out of space. And starting from there, we take this, we set it equal to 0, and we solve. So we're going to get 4 is equal to 90,000 over X squared. We multiply both sides by X squared to get 4X squared equals 90,000. Divide both sides by 4. X squared equals 22,500. Take the square root of that. If you look at it, most of you are probably just going to use your calculators, but if you look at it, 225, if you remember from high school, well, that 15 squared is 225, and then here this is 100, so that would, you could multiply it by 10, so you would get 150. If you just want to use your calculator, go ahead. So that's going to mean that our total cost will be at a minimum when our X is equal to 150. So if that's the case, that's the quantity. Again, X was the quantity that we want to order. So we're going to have minimum cost when we order 150 cases per order. Well, how many times per year must we order this? Well, now we go back and use our formula that we developed before. The R is equal to 1,200 over X. And if x is 150, it becomes 1,200 over 150. So we're going to order 8 orders per year. So 8 orders per year at 150 cases per order. That will give us our 1,200 cases that we need. It will also give us our minimum inventory cost. Now this problem consisted of finding the economic order quantity. And the economic order quantity, the book refers to it as EOQ in the homework. It's simply the quantity or the amount that you need to order in order to minimize the inventory cost. Now usually with this, they're wanting you to find not only the amount that you need to order, but also how many orders you need per year to have a complete answer. Now, here's another sample. A bookstore is attempting to find the EOQ for a popular book. They expect to sell 8,000 copies in the next year, and they figure that it costs $40 to process each new order for books. The carrying cost, apparently they're getting a loan out to find this, or to finance this, and the carrying cost due primarily to interest payments is $2 per book, and just to calculate the carrying cost based on maximum inventory. So that's why they have that here. How many times a year should orders be placed? And of course the follow-up question is, well, how many books should be ordered each time? Well, if we work with this, we know that our inventory cost is ordering cost plus carrying cost. I'm going to switch over. This is the same problem, but it simply gives more board space to work with. When we work with this, our inventory cost is our C of X. And that's going to be the ordering cost plus the carrying cost. Now when we're doing this, we look at the ordering cost, and they tell us that immediately. It costs $40 to process each new order. So the order cost is simply $40 per order, which is going to be 40 times R. R is the number of orders per year. The carrying cost, we're told up here that it's $2 per books. So it's $2 per book. But the method of inventory, it's based on maximum inventory. And maximum inventory, we said, was just simply X. So we multiply these two together to find that the carrying costs are going to be 2X. Now, our cost function then is going to be the ordering cost, 40R, plus our carrying cost, 2X. And of course we know this is what we're trying to minimize, so this is our objective function. And our constraint, again, this is what we're just simply supposed to know, that the number of orders times the quantity per order is going to equal the number of, in this case, books that we're going to sell throughout the whole year, which is 8,000. Since it's equal to something, we know that this is the constraint. Now, since we have the constraint function, we want to solve it for R or for X. I'm going to solve it for R. So R is going to be equal to 8,000 over X. Now we take this and put it into our other function, our objective function. So our cost function, we call it C of X or just C, I'm not that picky, that is going to be 40 times R, and now we're saying R is, again, this 8,000 over X, so 8,000 over X plus 2X. Now we're down to one variable, so we can start working with this. This is our cost function. We know we need to find the derivative, set it equal to 0, and solve. So let's do that. Our cost function becomes 320,000 over X plus 2X. And of course, if we're doing this, then we need to take the derivative of it. we need to change this to 320,000, x to the minus 1 plus 2x. And now we want to find our first derivative. And that's going to be, I'm going to work over here first just to keep it a little bit neater. And say that's going to be 2. And then it's going to be 3,200 times minus 1, so it's going to be minus 320,000, I need one more 0, times x to the minus 2. Now, we're going to set this equal to 0, but probably before we do that, we're going to convert 20,000, the x to the minus 2 to be minus 320,000 over x squared. Then we set this equal to 0, and now we solve. Now, if we do this, excuse me, get this working again. If we take the 320,000 to the other side, we're going to get 2 equals, the minus 320,000 becomes positive 320,000 over x squared. Then we bump it up again. We multiply both sides by x squared to get 2x squared equals 320,000. We divide both sides by 2 to get 160,000. Take the square root of this, and of course we realize, well, this is going to be 400. Oops, I forgot a 0 there. This is going to be 400. And this is, again, x, which is books. So in each order, we're going to order 400 books. Or to say that it's simply 400 books per order. Now, we have our x, that's how many we need. If we need to know our number of orders, we can come back to here. Our r is equal to 8,000 over x. So now we simply take 8,000 and divide it by 400, and we get 20. So again, this is the number of orders, so this is 20 orders per year. So when we're done, we realize that in order to have the minimum inventory cost for these 8,000 books, we're going to place 20 orders throughout the year and order 400 books per order. And let's switch back to our PowerPoint and go on to the next problem. Now, when we're working with this, this is an example. It actually is going to lead into our next class, so it's a helpful thing, but you'll see problems similar to this in the homework. Shakespeare's Pizza sells 1,000 large vegetarian pizzas, no meat, per week for $18 a pizza. When the owner offers a $5 discount, the weekly sales increase to 1,500 pizzas. Assume a linear relationship, a straight line relationship between weekly sales and the discount. How do we figure this out? Well, we realize, let's go back and look at what we already know. Well, when we charge $18 per pizza, well, we're trying to find a linear relationship between the weekly sales and the discount. Well, if it's $18, then there's a $0 discount, not offering any discount, in other words. So if there's no discount, when there's no discount, how many pizzas will we sell? We're trying to find a relationship between the weekly sales, the quantity of pizzas that we sell, and the discount. Well, the problem tells us that we're going to have 1,000 pizza sales. Now, if this is a straight line, hopefully we realize that we know one point on this line now, that when the discount is 0, we will sell 1,000 pizzas. If we turn this into a point, saying, how did you figure that out? Well, we're supposed to find the relationship between our weekly sales, our A of X, and the discount. Well, when we're doing this, if it's a straight line, we're looking at one point, we know that we're going to find a formula for this eventually, but if we're finding one point, we know that it's going to have an x value and a y value. Now, one point in this line, if one point in this line has an x and a y value, which one is which? Well, again, our a of x is equal to x comma y. If that's the case, what is x? And we realize, if we look at this, that here it says, find the linear relationship between the weekly sales, a of x, and the discount of x. Oh, well, another way to write that would have been that it's x and a of x to find this point. And that is literally x, and here it says x is the discount. So our discount has to be our x, and our a of x is the weekly sales. So that's why I put it in that order, but if you're not sure, check to see what they tell you what x is. If x is the discount, and we put the discount first, and then the sales. Now remember, the other key with this was to remember that we are looking at a relationship between sales and discount, not the price and the discount. The price and sales, but the discount and sales. And that's what's here in the problem. So now if this is the case, we can rather quickly solve for this. We have a point, we have a point, and we know that it's at 0, 1,000. Well, if it's at 0, 1, 1,000, then isn't that going to be, the 1,000 going to be the y-intercept? We go back, y equals mx plus b. When our x value is 0, then whatever our y value is, that's where it crosses the y-intercept, what our b is. So that becomes a quick way of doing this. But we know our b is 1,000, so what's our m? What's our slope? Well, we need a second point to figure this out. And we have that information. It says when the owner offers a $5 discount, so on our next point, we have a $5 discount, the weekly sales increase to 1,500. Oh, well, the sales is 1,500. So now we have 2 points, and we can use our slope formula for this. We can set this up. Our m is going to be our x sub 1, and let's use this one as our y sub 1 and x sub 1. So it's going to be 1,500 minus the 1,000 divided by 5 minus 0. And so that's going to be 500 over 5, which is going to give us 100. So we know that our slope is 100, so our formula becomes y is equal to 100x plus 1,000. And that's the relationship between the two. That's what we're looking to here. Our y, in this case, would be equal to a of x is equal to this. So now, we finally found what the linear relationship is. If you didn't realize that the point 0, 1,000 was the y-intercept, then you can just go back and use the point slope. You still calculate the slope of 100 and use one of the 2 points in the equation, and you end up still getting the same value. Now, I copied the value here to the formula here, so we still have access to it. Find the value of x that maximizes the weekly revenue. Okay, so we want to find what the maximum revenue is. We need to find our revenue function, take the derivative of it, set it equal to 0, and solve. Well, they give us a hint here, that revenue equals a of x times the price. Again, our a of x is weekly sales. Well, that kind of makes sense. The weekly sales, if we sell 1,000 pizzas at $18, we know how much revenue we're going to have, right? So, reminding us of this simple fact. A of x, which is 100x plus 1,000 times the price. Well, how do we calculate the price? Well, we're trying to find the price, right? And we know our A of x is 100x plus 1,000, but how do we calculate the price? It's different depending on the discount, right? Well, sure. If we look at this price, what's that going to equal? Well, if there's no discount, it's 18, right? If we had a $5 discount, then it would be 13. If we had a $3 discount, then it would be 15. Well, how do we know what this is? Well, we need to put an x in here somehow, right? And if x is the discount, the price is going to be 18 minus the discount. And if the discount is x, our price is simply going to be 18 minus x. So that if we give a $5 discount, the price will be 13. So just think that through a little bit and we come up with a formula. Price is equal to 18 minus x. Now I'm going to switch over again to this utility and move over to this problem. So we're working on the same one. Again, this is the same problem, and now we know that price, whoops, let me just copy it here, that the price is equal to 18 minus x. So our revenue, switch colors here, our revenue, or R of x, is going to be, again, A of x, which is 100x plus 1,000 times our price. And we said our price was 18 minus x. So now we just simply need to multiply these things out. 100x, I should use the mouse so you can see. There's different ways you can do this, which I'm just going to use the distributed method for something a little bit different. 100x times 18 excuse me, gives 1800x, and then with the distributive method you just take the same 100x times the other one, the minus x, to get minus 100x squared. And then we do the same with 1,000. The 1,000 times 18 gives us 18,000, and then 1,000 times minus x gives us minus 1,000x. If you prefer to use the FOIL method, that's fine. Just simply using something different. The FOIL method is an excellent way to do this. However you're used to doing it's fine. Now, combine like terms, and we'll find that this is equal to, whoops, maybe I should put them in order instead of just going straight. With the x squared first, it's minus 100x squared plus 800x when we add the 1800x and subtract 1000x plus 18,000. Now, this is what our R of x is. We want to calculate our prime of x, our marginal revenue. Well, minus 100 times 2 gives us minus 200x to the first power plus 800. And we know that we set this equal to 0 and solve. So now we simply do the solving. 800 equals 200x divided by 200 on both sides. Our x must simply be equal to 4. Again, 4x was our discount. So if that's the case, that means we would have a $4 discount. And that will give us our maximum revenue. Now, of course, we can go back and find out how many sales we would have by putting a 4 into our A of x here. So we'd sell 1,400 pizzas in that case. Our revenue, we would just go back to it and do an R of 4. So back into this minus 100x squared plus 800x plus 18,000. We can plug that in and find out. In this case, it works out to be that our weekly sales would be 19,600 in weekly sales. But again, whatever the problem is asking for is what you would use. In this case, they're only asking for a discount, so we could have stopped at a $4 discount, but we know we can apply it to other things as well. Now go back to PowerPoint. And the Coca-Cola problem. You'll see that it's part of the homework for today. Earlier, in the prior lesson, as I introduced optimization, I had said that if you had a billion cans that you were selling, aluminum cans, if you could save a tenth of 1 centes, of Lithuanian centes, that would result in a savings of 100 million liters per year. Well, if you work for Coca-Cola and you were able to save them 100 million per year, boy, I think you would get a raise, don't you? Well, is the Coca-Cola can minimized for cost? Excuse me. If this is a regular Coca-Cola can, maybe if it was just a little taller, and then hence the volume stays the same, it'd be a little skinnier. Maybe that would be maximized. If that would save 100 million liters, you would think Coca-Cola would be happy that you told them that, and they would do that. Maybe it's actually the matter that the can has to be very short and very fat, so to speak. It looks kind of funny, but maybe this kind of can saves on the metal. Maybe it saves even more than 100 million per year. And in fact, we know that they make more than $1 billion per year. Well, maybe a can that looks a little something like this would save Coca-Cola some money, or maybe it's a little bit wider and a little bit shorter. Well, how do we do this? Well, I should hand out in class, and it's also on Moodle if for some reason you don't get it. There is a sheet about minimizing material cost looking at a Coca-Cola can. And the actual can, we're going to assume that it is simply a cylindrical container. I know that the very top and the very bottom come in, but just to make it easy, let's just assume that it's, when we're doing this, the height is the full height and the radius is the full radius, and it's that way everywhere, at the top and the bottom, the same as in the middle. It just makes it easier. Now, the actual can of Coca-Cola, the sheet tells you how tall it is and what the radius is, and then it mentions that, oh, the can's not maximized. So, well, we could save Coca-Cola a lot of money if we could minimize, excuse me, I said maximize, minimize the cost of the material of the aluminum into making a can. Aluminum is rather expensive, so saving us a small amount translates into a lot of money. So the challenge is asking you to calculate what should be the height of it and what should be the radius or the diameter of the can to minimize the cost. If you're not exactly sure, the values for, you end up using the formula for volume and also the volume or the formula for surface area of a cylindrical container, and it's actually considered a right cylinder. So you can just look up the formula on Google. Right cylinder surface area formula, right cylinder volume formula, and you can find what you need, figure out which one you want to use where, and then you can actually find what will minimize the cost, because you're going to minimize the surface area of the can itself. You're not going to minimize the volume, because the volume is set based on the size of the can. So work with that. It's a little bit of a challenge. So I don't grade you based on whether you get a correct answer, but based on whether you try or not. And the second question says, well, we know what we will discover is that the can is not minimized, and hence not minimized for cost. So why? Why doesn't Coca-Cola change? They probably know this. It's not a hard thing to figure out. So why don't they try to save millions of liters, hundreds of millions of liters per year? And again, I'm not going to require you to find the right answer, just what do you think? It's designed to get you thinking. Just simply putting some thought into it would be enough to get full credit for the problem. I'll talk about this in class, so if you have any questions you can ask then. The homework for today, of course, we have some review questions from section 2.6. There is a challenge one if you really want to try the challenge. Again, they're always optional. And the Coca-Cola problem. It is, actually, all of this is on Moodle, and you can get the Coca-Cola problem there as well. Again, the Coca-Cola problem is something that will be handed in, so I would ask you to work on that. You'll have some time to do that, and in class I'll make it clear as to when you must hand it in. And yeah, this is the homework, so you can begin. And we'll see you in class.